Welcome to How to Succeed in ECE Without Really Trying. In this video, Dr. Victor DeBrunner will discuss computing Laplace transforms.
Today we are going to look at solving Laplace, finding Laplace transforms. From the definition, I'm going to use the table to validate the example and the way we work it, just so you can see how the definition and the table works with you. So we see here the problem. I want to find the Laplace transform of this double-sided exponential right here. So let's start first by describing that e to the minus absolute value of t. There are several things that we might need. Let's start with the fact that the absolute value of x is equal to x when x is greater than 0 and negative x when x is less than 0. So we can use that, of course, then to realize that e to the minus absolute value of t is piecewise linear in description. And by graph, when t is positive, e to the minus absolute value of t is going to be e to the minus t, which is a decaying exponential towards 0, and the function of that graph is e to the minus t. And when t is negative, the absolute value is negative x, so that then becomes e to the t. And of course, as t gets more and more negative, e to the t also drops to 0, and so we have a graph that looks like this. This can be written in a different fashion if we use the fact that u of t itself, the unit step function, is equal to 1 when t is positive and 0 when t is negative. And thus, e to the minus absolute value of t can also be written. So I have e to the minus t u of t to get the positive time part of that function. And for the negative time, I need the opposite. So I need u of minus t. And now we can look up here at the table where we have these two functions, and we now can see that I need either e to the minus lambda t u of t. So for that term, that first top row, lambda is 1, right? I have e to the minus 1t, so lambda is 1. So that term from the table is going to go over to 1 over s plus 1. And the e to the t, u of minus t, is the second row of that set. So I have lambda is equal to minus 1, right? Because I have plus e to the t, so I need e to the minus 1 times t. So lambda is minus 1. So that's going to go to 1 over s plus minus 1, and then I have the minus sign, so I need a minus in front of that. And normally, of course, you'd write that as 1 over s plus 1 minus 1 over s minus 1. if you look at the last column too, you can see that the S equals sigma plus j omega, right, our complex frequency. I need sigma to be greater than -1 and sigma less than 1, which we would normally write as -1 less than sigma less than 1, right? Now I'm going to use the definition to compute the exact same part. You'll understand more about what that region of convergence means and some things. So let's look at that. So I'm going to copy, right, using the definition. Then I have x of s equal the integral minus infinity to infinity x of t e to the minus st dt, which is equal to minus infinity to infinity e to the minus t u of t plus e to the t u of minus t, all that times e to the minus st dt, right? Just using what you see over here. Clearly, I should break that up into two parts. So I'm going to have the first part is the integral from 0 to infinity, e to the minus t. The u of t is what changed the limits, because u of t is 0 for all the negative parts. And then I have my e to the minus st dt. And then I have the second part. And again, I have u minus t, so I only get the part of t that's negative. And now I have e to the t, e to the minus st dt. I have those two parts. Normally, we would combine these, 0 to infinity, e to the minus s plus 1 times t dt, and then I have the other side, minus infinity to 0, and again I'm going to have an e to the minus s minus 1t, so I have e to the t and e to the minus st dt, right? And using basic calculus that you learn, these are just e to the at, so this evaluation then is e to, excuse me, I need to do the division, so I'm going to have minus 1 over s plus 1, e to the minus s plus 1 t, 0 to infinity, and minus 1 over s minus 1, e to the minus s minus 1 t, again minus infinity to 0. All right, this term then becomes minus 1 over s plus 1. I have e to the minus s plus 1 times infinity, and the 0 term minus e to the 0, which is 1. And the same thing happens over here, but of course e to the 0 is 1, and then I have minus e to the minus s minus 1 t, and t is minus infinity. All right. Some of you are looking at this and going, why do I put the infinity in there? Because e to the minus infinity or e to the plus infinity, you think you know, but the problem is s is complex, right? So I'm going to pull out my evaluation for a minute. So I have e to the minus s plus 1 infinity, and I'm going to put in e to the minus sigma plus j omega plus 1, evaluated at infinity. And you should realize that I have an e to the minus sigma plus 1 infinity and an e to the minus j omega infinity by rules of exponents. The e to the minus j omega infinity is bounded. It's just a complex sine wave at frequency omega. So the real part goes between plus and minus 1. The imaginary part oscillates as well between plus and minus 1. It's bounded. It doesn't get big. It doesn't get small. It just goes back and forth in this complex plane, admittedly, the real and imaginary parts, but both of them are bounded. So what I really need to look at to do the evaluation is the e to the minus sigma plus 1 times infinity. I need that to be a negative number, e to the minus some number times infinity. And so I need sigma plus 1 to be greater than 0, right? So that means I need sigma greater than minus 1, which is in fact exactly the top term here at the bottom. Same things, and when that's true, that term then goes to 0 and is gone. The same thing's going to happen to the e to the minus s minus 1 minus infinity. Again, plug in s equals sigma plus j omega and work it out. I need sigma less than 1 for that term to go to 0. And as soon as I have sigma in that range between minus 1 and 1, those two terms are 0, and then I have left I have minus 1 over s plus 1 times minus 1, and I have minus 1 over s minus 1 times 1, which in fact is 1 over s plus 1 minus 1 over s minus 1, which is exactly what we derive from the table.